In this lab, the goal was to model motion with constant acceleration. There are two equations central to these models. The first is Newton's second law. This law demonstrates how final velocity is the sum of the initial velocity and the change in velocity per second calculated in the second half of the equation. The force on the object divided by the object's mass multiplied by a period of time. There are two forces that will be acting on our object, the force of gravity and drag force. The first of these can be calculated through the equation for gravitational force, where force is equal to gm over r squared, where g is the gravitational constant, m is the mass of Earth, and r is the radius of Earth from the center to the surface. Through these calculations, the force of gravity is found to be 9.8 meters per second squared towards Earth. The drag force is more difficult to calculate, but it is essential to understand that it moves in the direction opposite of the motion. This would mean that it moves in the direction opposite of Earth's gravitational force. In our model of motion, we can expect the object to fall slowly at first and quickly speed up because of gravity. And this is because the force of gravity is a greater force than the drag force. We start at zero velocity and exponentially fall faster. As you can see in the tracker and the graph calculated using points found in tracker to the right, our predictions were correct. The graph is exponential and nonlinear. It moves in the negative direction because of the force of gravity is towards Earth, which is in the negative y direction in our model. The model follows Newton's second law because the velocity is constantly increasing in the negative y direction, which is what the equation predicts. In this next graph, we compare the data we obtained from the video and tracker with the calculated graph of what we should expect when factoring gravity and drag force. We found this graph using our computational model and calculating in the drag force. The observed data is in red, whereas the calculated data is in blue. Next, we have the computational model, factoring in only the force of gravity. As you can see, it is an exponential graph of distance, which is as expected. To create the graph, the main changes I had to make was changing acceleration. First, I changed the time frame of the movement to match the experiment. The most important difference, however, was the change of force. I changed it to mass times gravity in order to account for the gravitational pull. It had to be negative because gravity was moving towards Earth in the negative direction. I plugged in Newton's second law into the change in velocity within the while loop. After each iteration, the velocity will change by the value of the force divided by mass times the delta t. In our next model, we have to account for the drag force, which is the force of air resistance that acts in the opposite direction of the movement. The model is nearly exactly the same, except it shows the two forces acting on the object, gravity and drag. The coding was nearly exactly the same as for the gravity code, but it added one more variable, the proportionality constant b for drag force. Our models do not show any signs of terminal velocity. However, it would eventually be achieved if the ball continued to fall. This would occur when the drag force equals the force of gravity, making the net force zero. However, if the object was initially thrown down, terminal velocity would be the same, but it would just be achieved faster. The initial velocity would be greater, but the initial drag force would also be greater.